All right, welcome to video C13. In this video, we're going to look at geometric sequences as multiplicative or exponential structures. So learning goal is I can recognize a geometric sequence as a multiplicative or exponential pattern, use common ratio, and write a general term. So this is kind of the flip side of C12. So C12 was arithmetic sequences, which were linear structures. And that was nice because you'd seen linear structures before. So kind of looking back to Math 10. This video, we're going to look ahead to Pre-Cal 12, because Pre-Cal 12, you look at exponential functions. So a better understanding of geometric sequences now is going to help you next year when you're looking at exponential functions in Pre-Cal 12. So you can see the hook there. We have a sequence 3, 6, 12, 24, 48. So our question is just what is happening? Is what's constant, the amount being added or the amount being multiplied? And then if this were exponential, what that just means we have a constant multiplier. What would that multiplier be? So take a look, and then we'll look at this question in I do 1. Okay, so take a look at this question here. We see kind of pretty quickly it is multiplicative, right? Because if I look at the terms, if I'm thinking, hey, I think it's arithmetic, I'm going to say, well, T2 minus T1 is 3. T3 minus T2 is 6. Those are not the same, so therefore not arithmetic. Now, if I go geometric, well, I'm going to say, well, geometric is going to be, well, 6 over 3 is 12 over 6, which is 24 over 12. In all those cases, it's 2. So my common ratio is 2. I'm just doubling my term every time. So common ratio here is going to be 2. And my first term, I can see that first term is going to be 3. And I'll kind of write these with the variables. So R is our common ratio. So R is 2, and my term 1 is 3. So as I kind of take a look at this question, like building up my table, repeated multiplication, I'm going to say, well, so term 1 is going to be just 3. Term 2 is going to be 3 times 2 one time. Term 3 is going to be that first term times 2 twice, so like 2 jumps of 2. My fourth term is going to be 3 times my common ratio 3 times. So if I try to generalize this, I'm going to say, well, it looks up, I'm just multiplying by my ratio n minus 1 times. So 3 times 2 to the n minus 1 would be my repeated multiplication structure. So as I get that, that is Tn there. So Tn generally is T1 times the ratio n minus 1 times. So Tn for us here is 3 times 2 n minus 1 times. Now if I want T8, I'm just going to plug in 8 for n. So I'm just going to say, well, that's 3 times 2, 8 minus 1 times. So T8 is going to be 3 times 2 to the power of 7. 2 to the power of 7 is going to be 128. So 3 times 128, which is 384. Done. That's it. Yeah. So that is I do 1. So you can see that was a geometric pattern, which we'll see next year is exponential. And it's going to be kind of like the arithmetic video, exponential, geometric sequences or exponential functions with some restrictions, which we will talk about here in a minute. So as we go, pause as we're moving on to the same questions. I want you thinking, why is that exponent n minus 1 instead of n? Try saying that in words before moving on, and we'll move to you do 1. Pause it here, and we'll bring it back. Okay. So yeah, as you can kind of see, hopefully, the exponent's n minus 1 because your first term, just like the linear, it's not your y-intercept, it's your first term. So it's kind of like you're starting to count at 1. So at term 2, you've only moved 1 ratio away. So you're only like term 1 doesn't need to be multiplied by the ratio. So every term is kind of offset by 1. So term 3 only need 2 ratios because you already started at 1, you didn't start at 0. So something like that. So you do 1, you can see same structure, negative common ratio. So this one you're going to see alternating signs. So your terms are 5, negative 15, 45, negative 135. Same idea. I'm going to get you right. Find the common ratio. Find Tn, the general term, and then find T5 using that general term. So pause it, take a try here, and then we'll revisit this. Okay. So as you see this, so I'm going to first on the left here, I'm going to confirm, hey, that I do have a common ratio. It's negative 3. Now notice the negative ratio is actually okay. It doesn't mean the pattern's broken. It does make it less useful for us in exponential functions next year. We wouldn't love this, but it's okay. It can happen. It just means the signs are going to alternate, which is going to be weird. But yeah, it's okay. So as I do that, I find ratio is negative 3. That means my general term is going to be 5 times negative 3 to the n minus 1. And you see in green here, just kind of like I expanded the arithmetic sequences. I could expand the geometric sequence to look more like an exponential you'd see next year. So if I split out that kind of negative 1 term in the exponent, I could make this look like negative 5 over 3 times negative 3 to the n. I really wouldn't this year in geometric, but I could. That's the kind of analog to what I was doing in the arithmetic. And then for T5, I do have two options. First option is use my general term. So if I plug in 5 for n, I'm going to get T5 equals 405. Or I already have T4 and I have R. So why not just multiply my fourth term by R to get my fifth term? So negative 135 times negative 3 is 405. And that's it. So yeah, that's you do 1. Let's move on to the final question here, which is I do 2. So here's mine. So mine is kind of like comparing the two, linear versus the exponential structure. So I have two sequences. A is 4, 7, 10, 13. B is 4, 12, 36, 108. So for sequence A, we're asking ourselves, well, what's constant, what fits, and the same thing for B. So our kind of prompt here is, so what are we looking for? So who has a constant difference, who has a constant ratio, and then which one kind of connects to linear, which one connects to exponentials. So if we look at sequence A here, sequence A, I see that 4 to 7, I go up by 3. 7 to 10, I go up by 3. 10 to 13, I go up by 3. So in this case, we have a common difference of 3. So what's constant? The common difference. So common difference is constant, which means arithmetic. Common difference, which means arithmetic. So what that tells us is we're going to say, well, in this case, we're going to have Tn equals 4 plus n minus 1 times that difference, which is 3. And again, this does connect to the line. If we wanted to, we could kind of expand this out to make it look like a line. So y equals mx plus b. For sequence B, well, this time I'm going to multiply by 3 every time. So if I multiply by 3 every time, I can see I have a common ratio. So what's constant? The common ratio. Now the ratio tells me I'm geometric. I have a geometric sequence on my hands. So for the formula here, I'm going to say, well, I know Tn is going to be that first term, 4, times the common ratio of 3 to the n minus 1. So you can kind of see here, this right away does expose the structures, right? So for the linear, the common difference, arithmetic, I'm taking my initial term and I'm going to add my common ratio n minus 1 times. For the geometric, I'm taking my first term 4 and I'm going to multiply. You can see the bracket means multiply by my common ratio n minus 1 times. So that gives me my connection. So constant ratio is an exponential, it's repeated multiplication, or my constant difference is linear, it's constant addition, linear structure. And that's going to be it. So you can kind of see there's my checklist. And again, quick summary is going to be for you to fill out. But kind of like, again, just making the connection here. Arithmetic sequences are those restricted linear functions, right? So linear functions that are discrete, and the n has to be a natural number. I'm going to write this for both. So remember, n has to be a natural number, so like 1, 2, 3, and so on. No decimals, no negatives, no zeros. For geometric sequences, they have it's repeated multiplication, so they're restricted exponential functions, right? So same thing, they're exponential functions with the particular rules that n, that input, the term number has to be a natural number. So your final checklist there, things you're looking for. To be geometric, the ratio between consecutive terms needs to be constant. Am I right? Just to be geometric. Put the reminder there. So to be geometric. That common ratio R is the repeated multiplier. Your formula is going to be T sub n equals T sub 1 times R to the n minus 1. Because term 1 has 0 multiplications, that's why you're using the n minus 1 as we discussed. The domain is natural numbers, so 1, 2, 3, and so on. And then your transfer Q. And that's it. Thanks for watching.